All right, guys. Today we're going to look at something called resistance. I know we went over resistance the last couple of days via Ohm's law, right? So we can solve indirectly resistance of V equals IR. But, this equation is helpful, but it doesn't really tell me much about this value. Like, what is resistance? So, well, I don't know. What is it? Well, today, right, in the next 5 or 6 minutes, hopefully I'm going to tell you what this is, how it's about, all sorts of stuff like that. Well, let's think about things for a second. Well, if I'm going to make a circuit, it looks like I'm going to have some wire around it and resistance, right? The wire itself is going to have resistance. So let's take a look at a wire, right? What factors are going to go into the resistance, right, of a wire, right? Well, let's take a look. Wire. Would you think it has a length? I do, right? So length, what do you think about the length of the wire? Well, I'm going to say length looks like L, right? And I say, hey, if I make the length bigger, what's my idea? What do we think about the resistance of a wire? Well, if your guess is that you think the wire, that the longer the wire, the bigger the resistance, you are correct, right? So what about the length if I make the wire smaller? Well, if you think that the resistance is smaller, you're correct, right? Good job. Okay, so let's take a look. How are they related? Well, if I wanted to plot R and L, one goes up, this one goes up. One goes down, the other one goes down. So I'm going to say that that's a direct relationship. What else? What's another property of a wire? Well, I don't know. How about the area of the wire, right? How thick it is. Thin, thick, I don't know, right? So how about area, right? Well, let's suppose, and what do you think? If I make the area bigger, look, if I make a wire fatter, right, what I'm really doing is I'm giving more and more places for the electrons to kind of hang out, right? So what happens is, as I make the area bigger, the resistance gets smaller. Remember what resistance is? It kind of controls or limits the amount of electrons that flow. So the smaller the resistance, the more electrons or easier it is for electrons to flow around. How about if I make the area smaller? Thin wire, right? Thin wire is going to have a really big resistance because there's not a lot of electrons that are there. They're going to be moving around. How about if I take a look at how the relationship is, R and A? Well, look, one gets bigger, this gets smaller. Area gets smaller, resistance gets bigger. What does that look like to you? Well, we've seen this many times before. That's an indirect relationship. So what do I have? Length is directly related. Area is indirectly related. All right, so if I had a wire, it's got to be made out of some material, right? Well, let's just call it material. What is it made out of? Well, I don't know, copper, aluminum, gold, whatever, right? Well, this value, right, is called rho. That's the symbol. It's really resistivity. I'll write that in a second. So it is rho, the Greek letter rho. So just look at it at the reference table, right? So the reference table is going to give you everything that you need about the material, okay? Some materials just have less resistance than others. Last one in this is going to be the temperature. What do you think? Well, this one's not that intuitive. One would think that if I increase the temperature, right, I get things wiggling around, it's going to make it easier, right, for the electrons to flow. Well, that's not the case. As the temperature increases, so does the resistance. How about if I make the temperature really cold on the wire, right? Well, the resistance goes down as well. So here I have four factors: length, area, material, and temperature. Let's see if I can come up with an equation, right, an expression for this. Well, resistance of the wire is going to be equal to, well, hopefully you made the guess that it's directly proportional to the material, resistivity, right? It's what? Directly proportional to the length, and it's going to be indirectly proportional to the area, right? So here is my equation for resistance, where R is going to be resistance. That is going to be in ohms. Rho, this is my resistivity, right? This is going to be in ohms per meter. Resistivity and resistance is not the same thing. Resistivity is just a property of the material, okay? Like I said, some materials are better resistors than others, right? Okay, which means lower resistance is what I meant by that, right? How about the length? Well, that's going to be length, right? And that is meters. And what about A? Obviously, that's the area. Be careful, that's meters squared, okay? All right, so here are the factors that's going to go into, right, looking into the resistance of a wire. You might say there's no temperature there. Well, we make things nice and easy for the regents, right? we're going to say that hold the temperature constant. So when you go to the resistivity values, they're all going to be at 20 degrees C. So they're not going to mess around with that too much, right? So let's give you a real simple example, okay? So what do I have here? Let's do an example, right? So let's take a wire, right? Let's make it aluminum, right? No, scratch that. Let's make it copper. Sorry, guys. Let's make it copper. I have that one memorized, right? So let's say I have a 1,000-meter copper wire, right? Let's say the area is going to be 3.14 times 10 to the minus 6 meters squared. Hey, what would be the resistance value of this wire? Okay, R is equal to rho L over A. So where do I get this rho value, right? Or I should say the resistivity value. We get it from the reference table. So on your reference table, there's going to be a table of these values. It's on the electricity section, and it should be 1.72 times 10 to the minus 8 ohms per meter. How long is the wire? Well, it's going to be 1,000 meters. And what's the area? 3.14 times 10 to the minus 6 meters squared. Well, I did this already, right? So if we calculate the numbers, I get about 5.4 ohms. So there's the resistance value of a copper wire, 1,000-meter copper wire. Obviously, if I make the wire longer, this value is going to get bigger. If I make the area bigger, this is going to get smaller, etc. So here's what I'd like you to try. Why don't you try this problem by yourself, okay? And I think it's a pretty interesting one. Let's take a look at a normal light bulb that's just going to be in your house, okay? What does a light bulb really consist of? Well, not an LED, but let's call it an incandescent. Believe it or not, it's nothing more than a big tungsten wire, right? It's a normal material, right? Now, the tungsten wire that's listed on your reference table is at 20 degrees C. But what happens is, as I turn this bad boy on, right, we know that the resistance is going to get bigger. So I want you to use this value, 5 times 10 to the minus 7 ohms per meter. Obviously, if, right, the wire gets bigger, the resistance gets higher, right? So the question is, I really should say is, how long is this wire, right? How long is that tungsten wire inside the average light bulb that's in your house? All right, well, let's get an area. I'm going to give you an area. It's 1.26 times 10 to the minus 9 meters squared. Pretty small. And let's give you just a resistance value, normal resistance value of this wire. How long is that wire? I want you to figure that out, okay? So use my equation, R is equal to rho L over A, with those values, and see if you can come out with a length. I think you're going to be quite surprised. All right, that's it for today, and I'll talk to you guys tomorrow. Bye-bye.